Good evening, everyone. My name is Nilmoni Karak. I am a research scholar at IIT Kharagpur, and I am the PMRF NPTEL TA for the course Fourier Analysis and its applications. And this is week 9 interaction class, live class, and today we will so some we will first recall the week 9 content, and then we will solve some problem related to your assignment problem. Okay, so first start with uh, Lagrange polynomial. Okay, so this is sorry week 9. Okay, and so we already have seen what is your legendary polynomial, Hermite polynomial. Okay, so like that, so these are some dense polynomial dense subset in L2 space. Okay, and also yeah, so that polynomial are used like something for something like for making orthonormal basis. Okay, so similarly so Lagrange polynomial works, okay, or Lagrange functions. And so first we consider like Lagrange polynomials. Okay, so this is like denoted by ln x. Okay, so we will see what is ln x. Okay, and uh, with one with some weight function e to the power minus x by 2, this ln x e to the power minus x by 2, so this forms an orthonormal first orthogonal, okay, orthogonal basis, and so from where it comes ln x. So this is a solution of Lagrange differential function x y double dash plus 1 minus x y dash plus lambda y equals to 0. Okay, and this is like using power series solution, so you can find the solution. So the equation uh, has a polynomial solution, of course, something f lambda x. But if you find the Wronskian of two solutions, this is at origin, this is 0 at origin, so we have singular solution. So we don't have two linearly independent solution for this. Okay, for this case, so one solution and scalar time another solution. Okay, so another solution is scalar time first solution. Okay, and now orthogonality of the Lagrange function. the functions ln x e to the power minus x by 2, n is 0, 1, 2 and so on, is an orthogonal system of functions in L2 0 infinity. So that is we have 0 to infinity ln x lmx e to the power minus x dx equals to 0 for m not equals to n. Okay. Okay, now what is orthogonal polynomial in general? So the properties established for the legendary Lagrange-Hermite-Chebyshev polynomial are rather typical of classical orthogonal system for polynomials. Okay. So in general, if fnx is a sequence of orthogonal polynomials, then the zeros of fnx are real, distinct and lie in the interval of orthogonality. Okay. And the sequence, okay, let us if fnx is a sequence of orthogonal polynomials, then the zeros of fnx are real, distinct lie orthogonality. Second, the sequence fn satisfies three term recursion formula. Then zeros of fn and fn plus 1 interlock. We already have proved this for some system of orthogonal polynomials. Okay. So there is an analog for the Rodriguez polynomial for the system of Hermite, Chebyshev, Lagrange and other classical system of polynomial. A Lagrange polynomial arises when sequence 1 x square is subject to Gram-Schmidt process with respect to inner product on 0 infinity with weight function e to the power minus x. Okay. So these are like some general concept for orthogonal polynomials, and then we move to another new topic. This is abstract Fourier analysis in Hilbert spaces. Abstract Hilbert spaces. Yeah, so briefly we will recall. Okay, so sorry. Suppose H is your, so H is a Hilbert space and consider the orthonormal basis like this. Index set is lambda. Note that orthonormal basis. Okay, note that this lambda may be uncountable. Okay, so here we are not assuming countable only. Okay, and Hilbert space with uncountable index is huge. Okay, uncountable orthonormal bases are huge, and yeah, but this appears in some applications Fourier analysis and differential equation as theory of almost periodic function. Okay, we will like come to almost periodic function later. Okay, and let us see. So you have a Hilbert space and you have a orthonormal basis, so you can construct Fourier series, right? So let us see Fourier coefficient and Fourier series. So suppose belongs to H, V belongs to H, this is alpha Fourier coefficient of V with respect to orthonormal basis B. Now we would like to consider this series. So this is Fourier coefficient and this is V alpha is element. So but what is the interpretation of the series? Here the number of terms is not countable, because we generally we like consider this index set is uncountable. Okay, arbitrary this index set, so maybe countable, maybe uncountable. Okay, so. Now a lemma on uncountable sum. Suppose A alpha belongs to this is a family of non-negative real numbers. We define alpha belongs to this A alpha to be the supremum over the set of all finite sums finite sums n belongs to n and your alpha I is this is comes from lambda. Okay, so we define this is supremum over the set of all finite sums like this. Okay, finite sums alpha 1 alpha 2 alpha n, and this is arbitrary. Okay, and then we have a lemma. Suppose the sum means this one is finite, then all but countably many of the summands A alpha are 0. So the proof is straightforward. So suppose not, we will prove this by contradiction method. So suppose this is not like accountably many. So suppose not, then we define en for each n and the union en, so n equals to 0 to infinity. This is basically A alpha such that A alpha is get positive, so all are like included. Okay, and so one of this set en must, because this is in this is your uncountable, so one of this set en, so suppose en is uncountable. Okay, so now set of all finite sums A alpha n plus A alpha 2 plus dot dot A alpha n, so A alpha I belongs to En, this is cannot be bounded above so since this is not this is not bounded above, so this don't have supremum at all, okay, and which is contradiction. Okay, so then we have all but countably many of the supremum alpha are 0, okay. Oh, sorry, of the summoned A alpha are 0. Okay. Now next theorem is existence of Fourier series for this case. So in this setup, the existence of Fourier series. Suppose this setup means this is more abstract, right? This is more general. So, and x alpha belongs to index set lambda are the Fourier coefficient of V with respect to a given orthonormal basis B equals to, of course, V alpha alpha belongs to lambda, then this sum must be convergent, absolutely convergent. Yeah, actually square sum squareable, this sum is squareable basically, okay. Yeah, and the square is basically convergent, and all but countably many Fourier coefficient vanish. The series converges in H and its sum is V. Okay. So the proof can be found in your lecture video as well as in lecture notes. Okay. So this is the existence of Fourier series. This is a theorem. Okay. So you can like you can look at the proof, okay, and this sum basically is convergent, as well as this is converges in H is a Hilbert space, and it converges to V actually, okay. So V comes from H, okay, so H is complete, so that's why uh, this series converges to element in H, okay. Now separable Hilbert space Hmm. So you know what is separable matrix space? If a matrix space has a countable dense subset, then it is called separable matrix space. Similarly, Hilbert space is also a matrix space. The concept is same. So if we have, so suppose H is a Hilbert space. If H has a countable dense subset, then H is called separable space, separable Hilbert space. Okay, and so here we can like think, um, so this dense subset collectively like comes from Gram-Schmidt process. Okay, so so suppose this H is a Hilbert space. Hilbert space, basically separable Hilbert space, then it has a countable dense set d1, right? Now we take a linearly independent subset d2, this is in d1, such that linear span d1 equals to linear span d2. Okay, so we can have this. Okay, then d1 is contained in linear span of d2, and this is dense in H. Because this is dense in H, now so by Gram-Schmidt process we get d3 such that d1 containing linear span d2 equals to linear span d3. And actually so this and continuing we like do this process, the same process, so we have the following theorem actually. Every separable Hilbert space has a countable orthonormal basis. Okay, and yeah, so example is your L2 AB or L2R. An orthonormal basis you can consider legendary polynomials, Hermit functions, legendary poly with a equals to -1, b equals to 1, and Hermite function as well. Okay, now let us talk about non-separable Hilbert space. So, so like, do non-separable Hilbert space exist actually? Yeah, and they are useful or not? Okay, so these are main questions. Okay, and yeah, actually they are useful, and yeah. So to study this non-separable Hilbert space, we need to know the concept about almost periodic function. Okay, first almost periodic function. A continuous function a from R to C is said to be almost periodic function periodic if for every epsilon greater than 0 there exists L epsilon greater than 0 such that every interval of length L epsilon contains a point C such that okay. So in particular for each epsilon greater than 0 there is a epsilon approximate periodic C. So period C with period C. Okay. So this ape, the almost periodic function is uniformly continuous. Uh, an AP is and the set AP of almost periodic functions on R is a vector space which is closed under pointwise multiplication and also closed under uniform limits. Okay, this will this will be needed in our this will be needed to solve some problem. Okay, so yeah, so vector space which is closed under pointwise multiplication and also closed under uniform limit. Okay, uh, Now next definition, mean value of an periodic function. Suppose f belongs to ap, means f is an almost a periodic function, then the limit t tending to infinity 1 by 2t minus t to t f x plus t dt exists uniformly with respect to x, and it is independent of x. This limit is called mean value of f. Okay, and also this definition f comma g, this is m f g bar. Okay, so first of all this is called your mf. Okay, so here the norm f, with this norm, this is an inner product in ap, and this is a pre-Hilbert space. Okay, now we will see a spectral theorem. Okay, so to see for spectral theorem, we first talk about compact operator on Hilbert space. Okay, recall the definition of bounded operator. An operator T h to h is said to be bounded, continuous if for all x belongs to h. Yeah, in other words, you can say the image Tu is of the closed unit ball U in H is bounded in H. But compact operator are like stronger. Okay, stronger. So definition. let H be a Hilbert space. Okay, an operator th to h is said to be compact operator if the image tu of closed unit ball u in H is pre-compact in H. Okay. This is note if H is finite dimensional then every operator on H is compact. We now look at a more interesting example for compact operator on Hilbert spaces. So this is called Volterra operator. So consider T L201 to L201 given by T of fx equals to 0 to x ft dt. The operator, this operator arises when we try to solve the IVP fx y0 equals to 0. Since f is in L201, so its integral Tf is a continuous function. Because you know the integration you can so this is differentiable, right? So f is differentiable, and so that's why Tf should be continuous. Okay, so well, x we assume x less than y, then T of fx minus T of y, and this is less equals to integration x to y mod of ft dt, and this is less equals to x minus y. So this Volterra operator is compact, right? So to show this, uh, we assume first norm a plus equals to 1, okay, and for all f a unit ball u in L201, um, so for this we need Arjola-Ascoli theorem, okay, or Ascoli-Arjola theorem, okay. So this is a concept for equicontinuous function, okay. mm, yeah, one can check, and let us see. So basically I am not showing this is compact operator. So basically you have to see this tfx, right? So this tfx, this tf, this collection f belongs to u, okay. So yeah, norm f less equals to 1, and so that tf, f belongs to u, and if it comes from unit ball, like, okay, so that's why, yeah. So this is pre-compact, okay, and this can be shown by using Arjola-Ascoli theorem, okay. Okay, one can check from notes or lecture videos, and then more examples of compact operator. Okay. So previous example can be generalized, okay, uh, to other integral operator. Okay, so like Hilbert's meet. So Hilbert. Wait a minute. Yeah, so we can generalize the previous operator, Volterra operator, this to a Hilbert-Smith operator, uh, plugging a continuous function kxt in 01 to 01, and then also this mm, mm, new operator, tfx equals to 0 to x, kx, sorry, 0 to 1, okay, kx t ftdt, and this is again a compact operator, okay. And you know this Hilbert Smith operator has a connection with boundary value problem, okay. Wait a minute, just. So Hilbert Smith operator. Again, this operator is uniform operator, compact operator, and one can so um, this operator can be shown compact operator easily because yeah, for x minus y less than delta we have we have wait a minute. Okay, okay, and we have this t fx minus t fy less equals to 0 to 1 kxt minus kyt uh, ft and this is less than epsilon. Because this is continuous, uniformly continuous on compact set, epsilon 0 to 1 ft less than epsilon, and and uh, and so to show uniform boundedness, tfx, so m is supremum kxt over your 0 1 cross 0 1. Hmm. And this is m time norm of f, and this is m because we consider norm of f less equals to 1 initially. And similarly, now Arjela-Ascoli theorem prove this operator is compact actually. Okay. Actually, solving some differential equation, we will have this yx is basically y to 1, 0 to 1, kxt y to 1 minus k1t y to x time ft dt equals to 0 to 1 gxt ft dt. And here gxt, this gxt is called green function for the boundary value problem. Okay, and it is continuous, and the solution of the problem has been expressed as a Hilbert-Smith operator on L201. Now one can study symmetry of green function and self-adjoints. Okay, so let us recall what is self-adjoint operators on a Hilbert space. Okay, recall that if A is an n cross n symmetric matrix, is an n cross n symmetric matrix, then ax comma y equals to x comma ay for all, and the definition of self-adjoint operator on a Hilbert space is built on this. Okay, and similarly a bounded operator T from H to H on a Hilbert space H is said to be self-adjoint if tx comma y equals to x comma ty for all x. Okay, next theorem is there. Suppose kxt is continuous 101 cross 01, then the Hilbert Smith operator T L201 to L201 given by Tfx equals to kxt ftdt. Self-adjoint if and only if kernel is symmetric. Okay, I am not going to prove this. Here some equivalent statement. Mm, if if t Rn to Rn is a linear map, then the following are equivalent. So 1, T is injective, T is surjective, if infinite dimensional spaces the above equivalence fails. Okay, so for infinite dimensional spaces the above equivalence fails. Hmm. let H be a Hilbert space and T H to H be a continuous linear map. A complex number lambda is said to be in the spectrum of T if at least one of the following holds: T minus lambda I is fail fails fails to be injective. T minus lambda I is fails to be surjective. Okay, now we stop here and let us start to solve some problems. Okay, related to assignment problems. Okay, question 1. The differential equation cos x has only periodic solutions for all rational values of a, has only almost periodic solutions for all irrational values of a, C has only periodic solutions for irrational values of a, has only almost periodic solution for all rational values of a. Okay, so first we need to solve this differential equation. So y double dash plus y equals to cos x. Okay, so the initial equation is this equals to 0, so a plus minus I, so your complementary function, this is your c1 cos x plus c2 sin x, and yp is your, so see, when a equals to 1, this is different, and So when a equals to 1, so d square plus 1 cos x. How to deal with this? So this is your real part of 1 by d square plus 1 e to the power ix. This is real part of, so e to the power ix
क्रुशियल रोल ब्रो आपके तुम्हारे इधर आता ही नहीं है ना क्रुशियल रोल नहीं तो सिलेक्शन विनिंग टीम
yeah, so d plus I square plus 1 1, real part of e to the power ix. So this is your d square plus 2id minus 1 plus 1 is 1, and this is real part of, so 1 by d is common and d plus 2y 1, and e to the power ix is there. Real part of e to the power ix 1 by d, and like 1 by 2y is common, and 1 by 1 plus d by 2y 1, and then real part e to the power ix time 1 by d 2id, and this is basically inverse if you take inverse. So yeah, 1 plus x 1 minus x and plus x and so on, so this will keep 1, and the real part of e to the power ix, so this I and I, so this I and I square, this is minus, and x is there. What is the real part of this? I times minus x by 2, I time cos x plus I sin x. So this is basically x by 2 sin x. Okay, real part to this, and a real part of, and this is, and for a not equals to 1, this yp equals to 1 by d square plus 1 cos ax. So your a is not equals to 1, so this simply you can write, and real part, no, so basically, so this simply you can write cos ax by, so since a is not equals to 1, right, so yeah, 1 minus a square, so we can put the value of d as so a, okay, and minus a, d square is minus a square, okay, yeah, and then so finally yx is big c1 cos x plus c2 sin x plus x by 2 sin x if a equals to 1, and c1 cos x plus c2 sin x plus cos ax by 1 minus a square if a not equals to 1. So one thing you can check, so this is your, so a is a rational number, and one is, sorry, a is one is a rational number, and yeah, so this is definitely a periodic function, right? It's a constant time this, and basically this is your uh, almost periodic, okay. So for any irrational, But for rational case, this is a is 1. For example, if you take a equals to 1, so we will have like, so this is not a, no, not a like a periodic function at all, or almost periodic function at all, because x is there. Okay. And so your has only periodic solution for all rational, so this is wrong. You just take a equals to 1 and has only almost periodic solution for all irrational values of a. Yeah, since this is a almost periodic solution, so yeah, so we have for like, except a not equals to a equals to 1, so we have the solution is this is periodic, so this is also almost periodic, right? So this is true for any irrational. And not only periodic, sorry, not only periodic, so this is wrong by b. And has only almost periodic solution for all rational values of a. No, a equals to 1, this is not true at all. Okay, so b is correct. Okay, next solution, next question. Consider the function at given by minus infinity to infinity e to the power I dj square plus 1 dj on the value of a log pi. Okay, actually previously we have seen, so okay, solution at equals to minus infinity to infinity e to the power I dj by j square plus 1 dj. So if you see carefully, this at is nothing but the Fourier transform of this. Okay, okay, and the Fourier transform of this is basically the integral minus infinity to infinity cos tj 1 plus j square tj. And this yeah, this is actually pi to the power minus mod t. Okay, one can check. Okay, so we already have seen previously. Okay, and this is, so then, so a of log pi, this is pi time e to the power minus log pi, this is pi time 1 by pi, this is 1. Okay, now question 3 is the function xp minus mod t ap Very interesting question. So pi mod t we already have seen. This is minus infinity to infinity cos chi square plus 1 dj. Okay, and we can write this like, so actually this comes from some algebra, in algebra formula, so from AP. Okay, and minus n to n, okay, if all the minus n uniformly to t. So basically it is now sufficient to show each SAP, but this is Riemann integrable, right? This is the uniform limit uniformly limit Riemann sums. And this is okay. This is j minus 1 to j tilde. Okay, and since this is the finite linear combination of AP, and so this is the finite linear combination of AP, hence the uniformly limit minus n to n cos tj by 1 plus I square tj is AP, and hence this e to the power minus mod t, so 1 by pi is also, so is also AP. Okay, next we will see one last problem. Okay. GXT for the IVP. Namely, the unique solution TF is given by then the value of G99 100 plus G no sorry sum m equals to 1 to 100 G m to m plus 1 plus G m plus 1 to m. Okay. Okay, let us solve. So y dash x equals to, so y double dash equals to f, so right, so y dash x equals to 0 to x f dt, and then yx equals to 0 to x dz and 0 to z f dt. This is simple. And by parts, so first if you do so with respect to this and this will give 0, and then minus 0 to x dz, not dz, sorry, dz is z your integration, and okay, z and fz dz and plus, yeah, we are trying to do, like the derivative of this integral is fz, okay, and plus now x, this integral is x, and 0 to 1, not sorry, 0 to x f t dt. So this is x minus z 0 to x fz dz. Okay, so finally gx okay, this is x actually, I made a mistake. Okay, this is basically your x minus z No, so sorry, this is 1. Okay, yes, x minus z, that's why this is this can be written as like this, x and 0 z greater than x. Now this sum m equals to 1 to 100 gm m plus 1, so plus gm plus 1 m. So always this is 0 because if z is greater than x, so m plus n is m plus m is always m greater than m, so this is always 0. So this is m equals to 1 to infinity g m plus 1 to m, and this is m equals to 1 to infinity, sorry, 100 100 100, and this is x minus z, right? So m plus 1 minus m, this is m equals to 1 to 100 1, and this is 100. Okay, so answer is 100. Okay, so now I conclude this session here, and I hope it was a good session, and and yeah, next week at the same time, um, on Sunday at 7 p.m. we will meet again to discuss some problem related to your next week. Okay.